Let's start with the next part. Today we'll be studying about mechanical energy. Okay, do you know what is mechanical energy? Okay, good. Potential energy and kinetic energy are known as mechanical energy, right? So mechanical energy are of two types. One is potential energy and kinetic energy. We'll be studying about them in detail, but potential energy is basically because of height, okay, at what position you are in, or because of your mass, all right? And kinetic energy is due to the motion. If you are in motion, we say that you possess kinetic energy. Potential energy are of two types: gravitational energy and elastic potential energy. Kinetic energy are of three types: translational, then rotational, and finally vibrational. All right, we'll study about them in detail, but these are the types of energy. Mechanical energy are of two types: potential, kinetic. Potential energy is of two types: gravitational, elastic. Kinetic energy three types: translational, rotational, and vibrational. Let's see the first one, that is potential energy. Now, what is potential energy? Potential energy is the energy that a body possessed at the state of rest. Okay, like how you all are. You're in the state of rest. So you all have some form of potential energy. All right. It is due to two things. First is the position and size. Size means mass. So it might be due to your position or due to your size, and it can be due to the shape as well. So let's see the first one, that is potential energy due to position or size. So imagine you are standing in front of an Eiffel Tower. Okay, let's say that you are at a certain height, right? So if you're at a certain height, obviously the gravity will have a force of attraction on you. The gravity will try to pull you down. This force of attraction brings potential energy to your body. So you will have potential energy. Why? Because the earth is constantly attracting you towards itself. All right. But if, let's say, you have someone who has more mass, right? So the person with more mass will also have gravitational potential energy, but obviously more than you. So this is known as gravitational potential energy. Is it clear? Okay. So gravitational potential energy is due to the position or size. The higher you take one person up, right? So the gravitational potential energy will increase. If your size is more, then your gravitational potential energy will also increase. Few more things before we move on. Gravitational potential energy is always negative. Okay, now why is it negative? Because the gravitational potential energy is defined as the work done in bringing a mass to a height h. So whatever is the work done in bringing a mass to a height h, that is known as gravitational potential energy, right? So since you have to bring the person up, if this is the ground and this is the person, since you have to bring the person up, obviously you're doing the work against the force of gravity. And we already know that if you do the work done against the force of gravity, it will be negative. Okay, then the potential energy is directly proportional to the height. It means what? It means if you increase the height to which the person is, okay, the mass is, the potential energy will increase, right? Okay, but potential energy is zero at an infinite distance. Can you tell me why? See, the first one, what did we say? We say that potential energy will increase as you keep on increasing the height, right? Right now we're in the second floor. If you go to the terrace, you'll be in the third floor. your potential energy will increase, right? If you can go higher and higher and higher up, your potential energy will increase. But if you are very far, okay, at an infinite distance, let's say out of the Milky Way, then we are saying that potential energy will be zero. Why? If the potential energy is increasing with height, so if you go very far, it should still increase, right? But we are saying that if you are very, very far, then potential energy will be zero. Can you tell me why? Yes? Gravity as in? Very good. Yes, very good. If you remember, I told you in the beginning that the gravitational potential energy is due to the force of attraction. Now, if you are very, very far, will there be any force of attraction? Will the earth be able to pull it towards you? Yes or no? It will not be able to pull you. So if it's not able to pull you, that means there is no force of attraction. That means the potential energy will also be zero. You got it? Okay. So let's see the equation for gravitational potential energy, right? So imagine you have a person, all right, and you have to lift her up. So obviously, if you try to lift her up, you need to apply some force, right? And how much force will that be? Force will be equal to m into g. mg, if you remember Newton's second law, force is mass into acceleration. And let's say that you increase by a height of h, right? Then what will be the work done? We know that the work done will be, last class we learned, work done will be mgh. And this work done is stored in the form of gravitational potential energy denoted by the letter U. Simple? Okay. Now let's see the let's see the potential energy with respect to the shape. Okay. Have you seen this before? Do you know what this is? Have you seen this?
Yes.
What is it called? Huh? Slingshots, right? What do we do with these slingshots? Huh? Attack people?
No, like to stretch that thing,
Yeah.
we put rock also.
Okay. Yeah.
Now when you stretch it, more you stretch, there will be more force.
Yes.
Yeah, with great force you hit somebody. If you
You
stretch,
so by somebody, something you can hit. No, why is aggressive? Yeah, so basically a slingshot, right? So it has a rubber on this end, and then you put a stone or something, and then you stretch it like this, right? And when you leave it, then the stone will move this way and might be hit your target, right? Right? So when you stretch it, does the rubber want to be stretched? No, right? That's the reason why you have to apply so much of force to stretch it. So when you stretch it, the rubber doesn't want to be stretched, right? And so when you stretch the rubber doesn't want to get stretched, right? So obviously when you leave it, the rubber wants to come back to its original shape. So when the rubber wants to come back to its original shape, it will pull the stone along with it, right? And the stone will move. As you know. So here, what are we changing? That energy that it has, the potential energy, is due to its shape. Yes, no, it has nothing to do with the height to which you are taking. So this is known as elastic potential energy. Okay. A very common example is a trampoline, right? Has anyone used ever a trampoline? Have you ever played one? Trampoline? Where? You just said yes for the sake of where? No. You've never played a trampoline. Where? Apart. Okay, fine. So when you play in the trampoline, what do? You jump on it. So when you jump on it, the shape of the sheet changes, but it doesn't want to be in that shape, and it wants to come back to its normal shape. That pushes you up, and if you're not good, you will fall. Okay. The next one is kinetic energy. Now, this one is a little bit difficult. So kinetic energy is due to motion. Potential energy is due to rest, right? You must be in the state of rest. But kinetic energy, you must be in the state of motion. All right. For example, look at this. Okay, a man is being chased by a cow, right? So obviously the man needs to run. So as the man is running, he's in the state of motion. So he will possess kinetic energy. Fine, that's very easy. But how do you define in physics? In physics, kinetic energy is defined as the amount of work done by the retarding force in order to stop the motion. Okay, let me explain again. Imagine this cow is running, all right, and you want to save the man. So what do you need to do to the cow? You have to stop the cow, right? You have to stop the cow. Now, to stop the cow, you must apply some force, right? That force is known as retarding force. Why retarding force? Because you're bringing the cow in the state of rest. So that retarding force, whatever work that retarding force does in displacement S before you stop the cow is known as the kinetic energy possessed by the cow. You got it? So higher the kinetic energy of the cow, the more force you will need to stop it. Yes or no? Did you get this? And the equation for kinetic energy is half mv square. So potential energy is mgh, kinetic energy is half mv square. So clearly it depends upon the mass and it depends upon the velocity. Gyan Purabo? Huh? No? No? But? I'm sorry? Oh, kinetic energy. Okay. See, the definition is complicated. Okay. How do you define kinetic energy? Just imagine that, Tanya, she's running on the road. Okay. She's running on the road. So when she's running on the road, she'll have a kinetic energy. But how do you define it? So in physics, we define it as so she's running and you need to stop her. So to stop her, you'll be applying force. Okay. Now you applied force, but Tanya may not just stop right then and there, right? Maybe she'll drag you a little bit more before she actually stops. You got it? So the force that you applied, okay, and Tanya will displace in this direction. So there'll be a displacement and force. So you'll be doing some work, right? Work done will be what? Force into the displacement, a retarding force, some minus. Retarding force multiplied by the displacement. This work done is said to be the kinetic energy for her before you stopped her, that is. You got it? Definition is complicated. Yeah. Let me just see. Can I do this? Force is equal to ma. S is v square minus u square is yeah. That's how we come up with the equation also. See, Elizabeth? Work done is equal to force into displacement. Then force is ma, Newton's second law, mass into acceleration. And S, if you find from this equation, if you remember class 9, v square minus u square is equal to 2as. From here, you'll get S is equal to v square minus u square divided by 2a. But v will be 0 because you've already stopped Tanya. So final velocity will be 0. If you plug it in here, then a gets cancelled and you end up with half mu square. Okay, that's the equation of kinetic energy. You got it? So I've just derived it for you, but you don't need to know. I don't think there's anything, right? It's very easy. Let's look at the types of kinetic energy. So if you remember, there are 3 types of kinetic energy. First is when the body is moving in a linear path, straight path, like a car. Then it has something called translational kinetic energy. If you focus on the wheels of the car are rotating about a pivot. So it will have rotational kinetic energy. And the last one, the strings of the guitar. When you play the guitar, the strings vibrate, right? So when it vibrates, it has vibrational kinetic energy. You got it? Okay. Momentum is equal to mass into velocity. If a body is moving and you multiply the mass with its velocity, then what you get is momentum. All right. And kinetic energy, we already know. Kinetic energy, the formula is half mv square. All right. So what we are interested in is what is the relationship between them. You see, momentum also has mass velocity. Kinetic energy also has mass velocity. So what is the relationship between them? Let's try to find out. Let's take the momentum formula. P is equal to mv. From here, let's find v. So what will be v? V will be P upon m, right? And let's substitute that in the equation of kinetic energy. So kinetic energy is what? Half mv square. Now if you substitute v here, what do you get? Half m v square. So P by m whole thing square, right? Let's simplify this. So if you simplify this, we have half m times P square upon m square. M and square we can cut. So what do you get? P square by 2m. So that's the relationship. Kinetic energy is P square upon 2m. Right? Got it? Okay. The formula for momentum in terms of kinetic energy. So what will that be? If I'll write this again, P square by 2m. We want P. So if you take this here, we get 2mk is equal to P square. Square, if you take it this side, it becomes root over 2mk. So this is kinetic energy in terms of momentum, and this is momentum in terms of kinetic energy. All right, please copy this down. There, you can see, right? You didn't answer what I asked. Okay. Yeah.
That like we want to MV right mass into velocity.
Mhm.
So what if we take the velocity on the other side and leave m and then place the value of m, that kinetic energy?
That's also good, but we don't want to do that. We want to substitute v here, okay? Because velocity is something that is very difficult to measure. No, imagine a cow is running in front of you. How will you measure its velocity? Very difficult. No, you'll need a gun to measure velocity. So that's why we try to remove the velocity from the equation. Okay. Okay. Good. Good, Raghav. I always forget to bring chocolates. To bring. I forget, Tanisha. So the relationship is, first we have P is equal to root 2 mk and kinetic energy is P square by 2m. These two relationships are important to understand the next situation. Imagine you have an elephant, okay, let's say A, having mass m and momentum p, and you have a mouse B, mass small m and momentum p. So you can see both of them have the same momentum, right? They have the same momentum, but which one do you think will have more kinetic energy, the elephant or the mouse? The mouse. Mouse. Elephant, okay. Okay, let's find out. To find out who will have more kinetic energy, no? You have to find the ratio of kinetic energy of A, that is elephant, divided by kinetic energy of B, that is the mouse. Now, how will you calculate the kinetic energy of the elephant? It will be half into m into velocity squared, right? Oh, sorry, we'll not be using this equation because we don't know the velocity. So we will use the other formula. Kinetic energy, how is it related to momentum?
P square by 2m.
P square by 2m. But for A, m is capital M. For B, since momentum is same, it will remain P square by 2 small m. Do you understand this? Do you get this, everyone? Okay. Then I'll convert this division to multiplication. So what do we get? P square by 2m multiplied by 2 small m divided by P square. So we can cancel P square and P square, 2 and 2. So what do we get? Small m by capital M. Is it fine? Yes? So now you see, finally we got what? Kinetic energy of A divided by kinetic energy of B is equal to small m by capital M. So now, out of small m and capital M, which one is greater? Out of small m and capital M, which one is greater? Capital M, right? So since the capital M is greater than small m, here this is greater means here this will be greater. Denominator is greater on the right side, so denominator will also be greater on the left side. So that means kinetic energy of B will be greater than kinetic energy of A. So this you have to remember. Okay, copy this. And if you didn't understand, please ask me. That means what? That means when momentum is same for two bodies, if the momentum is same, okay, more mass will have less kinetic energy. So higher the mass, lower is the kinetic energy. You can just remember this statement also, but this is for when momentum is same. All right. Then let's try to do the case 2, that is when they have the same kinetic energy. So can anyone tell me what will be the starting equation in this case? We want to compare their momentum, right? That is, let's say we have again the same story. That is, we have an elephant and we have a mouse. This time they have the same kinetic energy. So if the kinetic energy is same, how do we find out which one will have more momentum? What will be the starting equation? What should we start with?
2nk.
What should I write here? No, see, when you had to compare their kinetic energy, we wrote kinetic energy of the first one divided by kinetic energy of the second one. Right? You check your copy. Now when we have to compare the momentum, we will write momentum of the first one, momentum of A divided by momentum of B. You got it? Yes. So momentum is what? Under root 2, for A it is capital M, let's say MA into K divided by, for B is root over 2 small m B K. Then here we can cancel 2 K K. Then what do we get? PA by PB is equal to root over MA by MB. Till here should be fine. Okay. Now you tell me on the right hand side which one is greater, MA or MB? Yes? MA, right? Because A is the mass of the elephant, right? So it's more. So MA will be greater. So if your numerator is greater, on the left side also numerator must be greater. Okay. So since MA is greater than MB, that means PA must be greater than PB. You can just write here when kinetic energy is same. Okay. Higher the momentum, when kinetic energy is same, sorry, higher the mass, higher will be momentum. Or you can simply write momentum is directly proportional to mass when kinetic energy is same. And for the previous one, kinetic energy is inversely proportional to mass. Okay. Yes. Yes.
So I just want to ask some projection energy, right? Like every time some like when the body is at rest, automatically the potential energy will be reduced. Or like in other cases, like any other cases. When the body is at rest, it's still a potential.
Yeah, when the body is not at rest also it can have potential energy. Okay. For example, let's say this is the marker. It's in the state of rest, so it will have potential energy. But if I drop it, it will fall down. Now, as it is falling, okay, somewhere in the middle also it is still at a certain height, right? So it will still have potential. It is moving, so it will also have kinetic, but it will have both potential and kinetic as it is falling down. The moment it touches the ground, then the potential energy will be 0. You got
If
it?
we throw something,
What if you throw something where?
if we just throw it anywhere.
So if you throw it like this, then it's moving, so it'll have kinetic energy, but it is at a certain height, so it'll also have potential energy.
So everything in the world possesses both the energies at the same time.
Not everything. Like for example, are you moving? No. So do you have kinetic energy? No. But are you at a certain height? Yes. So you have potential energy only at this point. Okay. But if I throw you off the balcony from here, then you'll have both potential as well as kinetic. You enjoyed, no, him falling?
Awesome.
Okay. That's a very good question, Raghav and Sishan. Anyone else has any question? So what is the work energy theorem? So work energy theorem says that the work done, okay, by a force on a moving body is equal to the increase in the kinetic energy. All right, what is that supposed to mean? Let's try to understand this with an example. Okay, imagine there's a ball of mass m, okay, and let's say the ball is moving. All right, right when it is moving, let's say Ronaldo applied a force on the ball. So if a ball is moving and you apply a force on the ball, what will happen?
We move faster.
It'll move faster, right? The force will produce acceleration, right? And the ball will move faster. Yes or no? Now try to understand. Did you apply a force? Yes. So if you apply a force and there was a displacement, that means you have done some work. Okay. So Ronaldo has done some amount of work. Point number one. Secondly, look at the velocity. What was the velocity initially? U. What is the velocity now? V. So has the velocity increased? If the velocity has increased, that means there is an increase in kinetic energy. Yes or no? So that's what this theorem says, that the work done by a force on a moving body is equal to the increase in the kinetic energy, right? So if we have to write the statement, this is the work done, here is the increase in kinetic energy. So simple, work done is equal to increase in kinetic energy. Is it fine? Okay. Let's prove this. So what will be the work done? In this case, what will be the work done? If the force applied is F and the body moves for a displacement S. So what will be the work done? F into S. So that is the work done. And what will be the change in kinetic energy, or rather increase in kinetic energy? Increase in kinetic energy means what was the final kinetic energy minus what was the initial kinetic energy when you kicked the ball, when you applied the force. So when the velocity is v, what will be the kinetic energy? Half mv square. So half mv square. That's its final velocity. Before you kick the ball, the velocity was u. So what will be the kinetic energy? Half mu square. So that means the change or the increase in kinetic energy will be half mv square minus half mu square. This is fine. Okay. Then we can take common here. So half we can take common, m we can take common, and we end up with v square minus u square. Then if you remember your class 9 formula, v square minus u square is equal to 2as. So if you plug that in here, we have half m, v square minus u square is 2as. Then here 2 and 2 gets cancelled. MAS, that's what we're left with, MAS. This is mass into acceleration. Mass into acceleration is force into displacement. But force into displacement is what? The work done. So increase in kinetic energy is equal to the work done. Okay. Let's take a small test, okay, to wake yourself up. Okay, wake up. Clarissa, can you see? Where's your specs again? Oh, now you lost. Oh, last stage. Okay. I'll ask people, okay? I'll not just give it to the entire class. The kinetic energy of a given body depends on the dash, position, center of gravity, momentum, displacement. So I'll start with the sleepy people. Zishan, DJ. Number 3. Okay. Nafi. The kinetic energy depends on position, center of gravity, momentum, displacement. 1. The position. Okay. Clarissa? Momentum. Okay. Then rest were finally. Elena? The kinetic energy depends on momentum. Right. Momentum is correct. Kinetic energy does not depend upon the position. Okay. I'll give you an example. Imagine that this is a marker at this height and there's another marker at this height. So clearly their position is different. Yes or no? But both will have kinetic energy 0 because it's not moving only. Okay. So it has nothing to do with position, nothing to do with center of gravity, and nothing to do with displacement. Okay. But momentum, yes, because momentum depends upon velocity. So if velocity is there, momentum is there, and momentum is there, kinetic energy is there. Okay. And that was our formula only, if you remember. We learned kinetic energy is equal to P square by 2m. So you can see that kinetic energy is dependent on momentum. Okay. All right. Let's see the next one. When a bell fixed on a cycle rings, then what type of conversion is that? You have seen cycle bell, no? Tring, tring, tring. So what type of energy conversion are we doing here? Gravitational potential energy to sound, kinetic energy to sound, sound to electrical, sound to mechanical. Mary? Huh? Kinetic to sound. Okay. Tanya? Very good. It is kinetic to sound. Why? Because you need to move your hand or you need to move that, what do you call that, lever, right? So when you move it, sound comes. So kinetic to sound. Let's see the next topic. Have you ever seen these kind of device in Instagram, Facebook? I don't think you guys use Instagram only. Who uses Facebook? I'm so old. Have you seen this before? Never.
Yes.
You have seen? Okay. What kind of reels do you get, Elizabeth? These type of machines are known as perpetual machines. Okay. So what is it showing here? See, there's a ball here. The ball has potential energy because it has a certain height. The ball falls from here. So it'll have what kind of energy then? Kinetic energy. Then here the kinetic energy will be maximum because it has fallen to the lowest height. Then it will increase the height because of the momentum. There will be an increase in height. It will go up. So then you'll have potential energy. Then again goes here. Then what kind of energy will it have? Potential. Potential gets converted to kinetic, kinetic to potential, and the energy conversion keeps on happening. Okay. And they claim, if you watch reels, they claim that this will never stop. What do you think? Is it true? No. Why not, DJ? Because you forgot. That's a good reason. It happens.
This photo, there's nothing to stop it, but many possibilities comes if there's any external interference.
So if there is no external interference, this will keep going on forever.
Yes.
Okay. Anyone else? See, so much to learn just from a reel. I copied it from a reel only. Yes. Just looking at the image, you know that it is not happening. Wow.
So, how can it go? Like, how can the ball go down so fast?
That's your problem, seriously. The ball will go down. There's a hole. Oh, there's a hole. You didn't see the hole, no? That's why.
Can it go that fast?
Imagine that it goes that fast. It'll come up again. Something is launching it. Okay. You're having problem with the way it goes down or the way it goes up? The way it goes down. Okay, nothing's wrong with the way it goes down. But yes, there is something wrong with the way it is going up. Okay, I wanted to do this experiment very badly, but we don't have proper setup for it. So we're gonna just move on. This machine is actually against the law of conservation of gravity energy. This image is against the law of gravitation, against the law of conservation of energy. Okay. This image is against the law of conservation of energy. See, when the ball will fall, obviously there will be some sound, right? You can hear, no, when the ball will fall. So there will be sound energy released. Again, when the ball is moving down, there will be some air resistance to the ball, and the ball has to move that air aside in order to fall down or go up. There it will lose some energy, right? Those energy that is lost is known as degraded energy. So whatever energy that you started with will not be equal to the energy that you have, right? You will lose some energy. Are you getting? Actually, what DJ is saying is kind of right. There's actually a machine here that increases its velocity and goes here. It is run by a battery. Okay, that is conservation of energy. Sorry? Yeah, you're a genius, DJ. So what does it say? Energy cannot be created or destroyed. It can only be transformed from one form to another. All right. That is conservation of energy. So let's prove this. Okay, imagine this Peter Griffin and he's falling from the sky. What kind of energy will it have as it is falling? Kinetic and potential. Good, Raghav. That was your doubt. It'll have both kinetic energy because it's falling, and since he's at a certain height, he will also have potential energy. All right. Let's prove the conservation of energy with a simple example. Imagine that's the guy of mass m. All right. Let's say that he is at a height of h from the ground. Let's say that we have just paused him there. Okay. So it'll have two types of energy. What will be the two types of energy? Let's say this is point A. So at A, what will be his potential energy? 0? No, it will not be 0. He is at a certain height, right? What is the formula of potential energy? That's done, mgh. Potential energy will be mgh. Okay? Okay. What will be his kinetic energy? Imagine that he's not falling. He's at a certain height. What will be his kinetic energy?
He's not falling.
He's not falling.
0.
His kinetic energy will be 0. So what will be his total mechanical energy? Total mechanical energy is potential energy plus kinetic energy. So potential energy is mgh, kinetic energy is 0. So total mechanical energy will be mgh. Fine. So at point A, the potential energy is mgh, kinetic energy is 0, and total mechanical energy is mgh. Fine. Let's say that he fell by a height of h. Sorry, he fell by a height of x. So at what height is he now?
X minus h.
Very good. He is at a height of h minus x, right? So let's say that this is the point B. So at B, what will be his potential energy? It will not be mgh anymore, right? Because his height has decreased. So it will be
mgh minus x.
very good. mg, and the height now is h minus x. If you open the bracket, you get mgh minus mgx. That will be his potential energy. What will be his kinetic energy? Kinetic energy, what is the formula? Half
mv square.
mv squared. But do we know what is his velocity now? So let's find the velocity. We can use that same formula again. V square minus u square is equal to 2as, right? So v square is the velocity that we want to find. Initially, what was his velocity when he was not falling?
0.
0. So his initial velocity is 0. 2 Acceleration is due to gravity, so g, and s is the displacement. So by what height did he fall? No, currently at what height? By what height? X. So x. Then if you simplify v square minus 0 square is v square only, and you'll get 2gx, right? Substitute that back here. So what do you get? Therefore, kinetic energy is equal to half m, and v square is 2gx. So if you simplify, half and half gets cancelled and you get mgx. Did you get it? Yes? So what will be the total mechanical energy now? Total mechanical energy is always potential energy plus kinetic energy. Potential energy is what? This one. mgh minus mgx plus, what is this kinetic energy? mgx. So mgx. Then we can cancel mgx and mgx. We're left with mgh. See, it's the same as when he was at a height h. Yes? So total mechanical energy is still the same. You guessed it again. Oh, very nice. Okay. So at B, the potential energy is mgh minus mgx. At kinetic energy is mgx. So total mechanical energy will be mgh. Right? Now let's see a final point. Let's say he fell all the way on the ground. Okay. But here we are assuming that he's just above the ground. Means, imagine that he has just touched the ground. Okay. We are assuming that he has just touched the ground. So let's calculate everything again. So this is the point C. At C. Now at C, what will be his potential energy? Very good. It will be 0 because the height is 0. So mgh, h is 0. So its potential energy will be mg into 0, which is 0. Kinetic energy will be, yes, half mv square. So again, v square we have to find. So we can use the same way. V square minus u square is equal to 2as. V square we have to find. Initially his velocity was 0. 2 acceleration due to gravity is g. S. What is S now? S is the displacement by which he has fallen down. So it'll be how much now? Huh? It will not be h minus x.
H minus H
We are considering from here again. So by what height did he fall?
minus A.
No, not h minus x. We are considering from here, from the point A. It will be h. So it will be 2g h. So v square will be 2g h. Kinetic energy is equal to half m v square. So half m v square is 2g h. Half and 2 cancel, we get mg h. So what will be the total mechanical energy now? Potential plus kinetic. Potential is 0. Kinetic energy is mgh. So mgh. Again it is mgh. So that means what? Total mechanical energy at the peak is mgh. At the bottom it's mgh, and somewhere in the middle, right? We did not take a definite number, we just took x. So somewhere in the middle is also mgh. That proves that energy is conserved. It will always remain mgh. You got it? Okay. So anyone has any question, please ask me. It is also very important. Okay. Now this is something that is very important for the numericals. Okay, Irene? Numericals. This is something that's very important for numericals. See, at the peak, what is the potential energy? mgh. And kinetic energy is 0. But at the base, the potential energy is 0 and kinetic energy is mgh. Right? So sometimes what kind of question can come is, they will tell you find the kinetic energy at the base. Okay, without giving you the velocity. They'll give you the mass, they'll give you the height, and they will tell you what will be the kinetic energy at the base. So you have to remember this, that I can find the potential energy at the top, and that potential energy will be converted to kinetic energy. Is it fine? It'll make more sense when we do the numericals. Okay. Let's see a simple example, okay, of the same thing with a pendulum. All right. You remember your class 9? In a pendulum, what is this position called? Extreme position. And what is this position called? Mean. And this position will again be extreme. So try to see. Here the bob is moving from its extreme position to mean position. When it moves from extreme to mean, the kinetic energy will increase, potential energy will decrease. Just see this slide. Okay. Just see it once. It's going down, right? That means the potential energy will decrease, kinetic energy will increase. Now, as it is going up, its potential energy will increase because the height is increasing, and the kinetic energy will decrease. Just look at this for 2 seconds. If you don't understand, let me know what I'm trying to show. So basically, when it moves from mean to extreme, its potential energy will increase, kinetic energy will decrease. And if it is moving from extreme to mean, so extreme to mean, its potential energy will decrease, kinetic energy will increase. Right? Nice, very attentive, Tanya. Good, thank you, Tanisha. You got this? You got this? What I'm trying to show? Okay. So, how will the graph look like? Okay, if we draw the graph for energy versus the height, okay, let's say that the blue color is potential energy and the orange color is the kinetic energy. So as you increase the height, what will happen to the potential energy? It will increase. So the graph will look, oh sorry, so the graph will look something like this, right? As the height is increasing, the potential energy is also increasing. What about the graph for the kinetic energy? How will that look like? As you increase the height, what will happen to kinetic energy?
Go down.
It will decrease. So, as you increase the height, the energy will decrease. Okay. The maximum energy at this point can be calculated by the formula mgh. We know that at this point the total mechanical energy will be mgh, and at this point also the total mechanical energy will be mgh. It's just that here kinetic energy will be maximum and here potential energy will be maximum. And you can see that the two graphs meet at the middle. What do you think this point represents? Blue one is the potential energy, orange one is the kinetic energy, right? They both meet in the middle. What do you think this point is? Very good. It represents that the potential energy and kinetic energy are equal. And that equality happens at what? At height 4. So we can say h by 2. 4 because we have taken the height till 8. So the height will be h by 2. What?
4.
What 4?
X is 4 and Y also is 4.
Yes, x is 4, y is also 4. Let's just test your knowledge. Huh? Where? What? Where? Yeah, it will stop. After some point, it will stop. Okay, because see, no matter where you do it, if you tie the string on a rope, on a support, there will be some amount of friction, right? So that friction will cause it to stop. Fine. If it does not stop, then it will become a perpetual machine. Isn't it? It will keep moving forever. Makes sense. Who's beatboxing? You. Okay. Let's see the next question. A fast moving cyclist stops pedaling on reaching a hilly track. If he continues to move with the acquired energy, then assuming no loss of energy, which one will be true? His kinetic energy remains constant all the time, potential energy remains constant all the time.
Explain the question again, I don't understand.
Okay. There's a cyclist. Okay, there's a cyclist, and he moved up a hill. Okay, and here's a cyclist. Okay, I can't draw cycle. Then he went down. So as he is going down, which of the situation will be true? So his kinetic energy will it remain constant? Yes or no? If you're going down a hill, will your kinetic energy remain constant? No, your kinetic energy will keep on increasing. His potential energy remains constant. No, because as you come down, the height will constantly decrease, right? So potential energy also cannot be. His total mechanical energy remains or continuously increases, sorry. No, total mechanical energy can never increase, right? It will always remain the same, and that is nothing but point number 4. You got? Okay, this is the board question, okay? Next one. This was also, I think this is 2024 question. Two identical marbles, A and B, are rolled down along the path 1 and path 2. So this is path 1 and this is path 2. Identical, everything is same. The slope is same, the curve is same, everything is same. The only difference is path 1 is frictionless, path 2 is rough. Okay? This is rough, this is frictionless, means very smooth. Which marble will surely reach the next peak? A or B? A. Why A?
Because it's smooth.
Because it's smooth.
It's only counted air resistance, not friction also.
Yes, very good. Right. You can see that this path is smooth. So there is a higher chance that this ball will make it to the next peak. Yes? Okay. Next. Along which path the mechanical energy will remain conserved? So along which path the mechanical energy will remain conserved? Path A or path 1 or path 2? So mechanical energy will remain conserved for A because it's following a smoother path, but for B it will be different. The total mechanical energy will not remain conserved because the energy will get converted to sound or heat. Right. So path 1. Last one. Along which path is the law of conservation of energy?
What?
Along which path is the law of conservation of energy? Wow. What should it be? What should it be? Last line. Along which path is the law of conservation of energy?
Being used.
No. Along which path is the law of conservation of energy applied?
So being used or applied same.
Law of conservation of
Answer will be both because
along which path is the law of conservation of energy? I don't know what this is. What can it be? Can you help me?
applied.
Applied is true. Is I like that.
Is being practically observed.
Is observed or is seen. Okay, I like that. So along which path is the law of conservation of energy observed? Path 1 or path 2? Zishan has already given the answer. It will be both because law of conservation will never change, right? It will remain the same. Okay. This was a horrible question. Oh, is there what? Oh, is being obeyed. Okay. Next question. Obeyed is the right word. If total mechanical energy is constant, why does a ball not return to the same height in real life after bouncing?
Because of the Wilson gravity.
How?
So because of when you're bouncing the ball, right? The gravity, right, is pulling the ball down.
Yeah, so if the gravity is pulling it down, then it will fall down, no? The question is asking that if the ball comes and it hits the ground, why doesn't it come back to the original height? But it will have certain energy. See, when the ball will fall, okay, as it hits the ground, right, that ball will get squeezed. So it'll have elastic potential energy, because of which it will be pushed back up. So if it is pushed with the same energy, then it should go back to its original height, right? Yes.
That example you gave of that real life pendulum example. So it is mean extreme, no? So from mean to extreme, this kinetic energy. So, but while kinetic energy is being converted to potential, there's some kinetic energy being lost. So because of that, there'll be more potential energy. So that's there'll be more potential energy. So,
So if there's
like
more
what-
potential energy means it'll come up?
No,
No. Just wait, just wait. Take it as a rest time. Okay. Yes, Tanisha. Very good. Oh, is everyone's becoming DJ or what now? Because there is dissipation of energy. How? Like? Very good. Yes or no? If you drop this, then if you drop this when it hits the ground, it makes some sound, right? So that energy came from where? It must have come from the potential energy. So there was some loss in energy. So when it comes back, it doesn't come back to its original height. Okay? I think that's what you meant, but you overcomplicated things.
sorry, sir.
It's okay. I'm doing the same thing today. Next. At the lowest point of motion, which energy is maximum and which is minimum? At the lowest point of motion means as the body is falling, this is the ground. Just before it touches the ground, which energy is maximum and which is minimum? Kinetic energy is maximum and let's stop for today. Your tiredness, no, somehow I feel like it gets transferred to me then. When I look at you guys now and I see you guys are tired and not understanding, no, I get nervous. Something wrong the way I'm teaching like that. Adasa is fresh. Huh? I should look at the camera. I'll put my own picture there and look at myself. Let's take a break. It's already 5:07. Then we'll start with maths. Can you please